Alright, we're back for our last video on atomic spectra. Let's say, for number 4, that an electron in the n equals 3 state, we want to know what sort of photons it can release and what their energies are. Well, n equals 3 means we must be looking at hydrogen. Those are the energy levels for hydrogen. So we come to the energy level diagram, and we see that n equals 3 is right here, 1.51 eV. Now, there are essentially two options for the electron at this point, if it's emitting energy. It can emit enough energy to go all the way back down to n equals 1 right now, or it can emit energy to go to n equals 2, and then later on emit more energy and go down to n equals 1. So essentially, there's three different energy releases that can be associated with an electron going from n equals 3 to n equals 1. So that means three different energies, photons of three different energies can be released over this process. So if it just goes from n equals 3 down to n equals 1, then the photon that gets released or emitted let's see, it starts off at negative 1.51 eV minus a negative. Let's see, it would go down to negative 13.6 eV. So one potential photon that could be emitted would have an energy of 12.09 eV. So that's just one possibility. Or we could have the chain of events where it goes from n equals 3 to n equals 2 to n equals 1. And in that case, you would get two different photons. The first one from n equals 3 to n equals 2, you can find the energy of that photon by saying the initial, again, negative 1.51 eV minus a negative. N equals 2 energy level is negative 3.4. So the energy of this photon, of one of the photons that gets released in this case, is 1.89 electron volts. And the other one would be the photon that gets released going from n equals 2 down to n equals 1. Now that negative 3.4 electron volt level, that's now our new initial energy level. And the final energy level is the negative 13.6. That is the energy level for n equals 1. And that is 10.2 eV. So there's three different photons that can be emitted of three different energies. And if you notice, it kind of makes sense that since we're still going from n equals 3 to n equals 1 in both cases, it kind of makes sense that the total energy, the combined energy of the two photons here equals the energy from just the one photon right there. Kind of makes sense. Number 5. How much kinetic energy will an electron in the ground state of hydrogen have if it absorbs a photon of 15 electron volts? So how much kinetic energy will it have that absorbs a photon of 15 electron volts? Now you might say, okay, so ground state means that there is that the energy level there is negative 13.6 eV. And you might say, well, there's no energy level that is exactly 15 electron volts away from it, so maybe this can't happen. Once you get past the ionization threshold, everything goes out the window. You can have whatever energy you want. You're no longer bound by that atom. So in this case, what happens is, if there's more than enough energy to ionize, then whatever is left over turns into kinetic energy. Okay? So whatever's left over turns into kinetic energy. And that only happens if there's enough energy to ionize. So if you have an electron in the ground state at negative 13.6 eV, well, it takes 13.6 eV to ionize. So if we do 15 minus 13.6 eV, we're left over with 1.4 eV. That turns into kinetic energy. 1.4 electron volts is left over, and that becomes the kinetic energy. Last one, number 6, very similar. What is the minimum energy needed to ionize a mercury atom that is in the C energy state? The C energy state is this one right here. The energy level is negative 5.52. If we want to just barely ionize this, basically meaning get it away from the atom but don't give it any extra kinetic energy, we just have to get it to that ionization level. How do we get it to the ionization level? We make its energy 0. If we have negative 5.52 electron volts of energy right now, if we add 5.52 electron volts of energy, then it should ionize. There you go. Those are just some different problems that you might see when we talk about atomic spectra. There's a great variety of problems you could see. The thing I did want to show you, though, is from a few videos ago. I talked about I talked about double slit diffraction, or the double slit experiment. So I want to show you this actually in real life. So if you come on over here. What we have, and this is a very basic setup, we have a little laser pointer right here. Okay, that's our laser pointer. We have a double slit. So what this is just a little piece of plastic, and you probably can't see it all that well. But if I zoom in, you can tell that there's actually two different little slits there. If you go out, it doesn't even look like it, but there are actually two different slits that light can go through. Okay? So, if I turn my laser on, I'm going to open the door here. If I turn my laser on, where are we? And it shines through the double slit, and granted you're not really seeing this very well because it's not at a good angle, but you see that there's a pattern on the wall. Now, before, when people thought that light was possibly made of particles, they would assume that there's just two little bright spots on that wall there. But that's actually not the case. You can actually see, I think, that there are some different fringes there, and I'm going to zoom in on that in just a second. So here's what I'm going to do. Give me one sec. All right. Let's just even this up a little bit. There we go. Okay. So all I've done is I put a bunch of books on top of the laser so that it'll stay lit. Still pointing through the double slit. Okay. Now remember, particle theory says that there should only be two little dots of light. Wave theory says that there should be multiple dots of light. Let's go look and see what the pattern is on that wall. Nope, I don't want to get in the way. As you can see, we have multiple fringes of light shining on that wall. What this is showing to us is the wave nature of light. Instead of just being two little bright spots, there are actually multiple fringes because the light is interfering, it's diffracting, it's spreading out through those two slits, and it's also interfering with itself to create multiple bright spots. I mean, I can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that's actually really good. 13 different bright spots. So, very interesting. Just another example, a really cool demonstration of the wave-like nature nature of light. But of course we know light is not simply a wave. It has properties of both particles and waves. This is just a demonstration of the wave properties. All right, I'll talk to you guys later.